Okay, good evening everyone. Welcome to One Concept Per Day portal. This question is taken from May 2002 paper, one of the very famous questions, and paper 2. And this question is about Rutherford's alpha scattering particle experiment. Okay, so though it appears to you that this question is somewhere related to Unit E of the current syllabus, but I still feel that this can be asked in mechanics and electrostatics. So this definitely is a wonderful question for those who say that I have mastered mechanics and who know something about electrostatics. Okay, you can try with this and you would have really learned a lot by solving this problem, because it encompasses a lot number of concepts together. Sub concepts are there. Okay, as I had already put in my post earlier. Okay, so look into it. So many concepts have been covered. If you know those concepts properly only, you will be able to attempt this. Okay, don't attempt it from the point of view of understanding this from Unity. But of course, in Unity, you study this as a theory, but you will be able to solve it as a practical question over here. All right, let's start with this. So this is about momentum and energy changes that takes place in the scattering of alpha particles. The diagram shows the path followed by a particular alpha particle that is scattered by the nucleus of a gold atom. When the alpha particle is in positions 1 and 4, it is far from the gold nucleus. Okay, so there is a gold nucleus over here, and this is your alpha particle. Alpha particle is nothing but it consists of 2 protons and 2 neutrons. Consists of 2 protons and 2 neutrons, and this is now moving towards the gold nucleus. Gold nucleus, when I say gold nucleus, this has a positive charge. Okay, which means electrons are already being removed out and you only have a positive charge. There is 2 protons over here, 2 neutrons. This is also a massive particle which is coming nearby to it. Okay, and now let us read the question. When the alpha particles position 1 and 4 from the gold nucleus, the respective masses are given over here. Okay, now what's happening to this particle? This particle always comes like this over here in a straight line. The moment it comes nearby to the alpha gold nucleus, what happens? There's a deviation being seen. Why does it get deviated? Because this is also positive, this is also positive. It gets repelled away. So hence it doesn't go have a head-on collision, but it takes a deviation. It goes away like this, right? See, it goes away like this over here. It doesn't fall into the nucleus. So it goes away over here. Okay, now we have understood the experiment. Indicate on the diagram the direction of the force acting on the alpha particle when it is at positions 1, 2 and 3. What is the direction of the force when it is at position 1, 2 and 3? That's the question. Now what is the direction of the force? When the particle is here, this is also positive, this is also positive. What will happen? There will be a repulsive force. So how will the repulsive force act? Repulsive force will act like this over here at position 1, right? Alpha particle is being repelled away from here. Now let us look at this point. Where is the repulsive force? It acts along the line joining the 2 particles. Here also you see line joining the 2 particles. So and then alpha particle, what happens to it? It is getting repelled away like this. So it should get repelled away like this over here. If it is getting repelled away, then what prevents it from going like this? Because it already has a velocity, so it takes a direction like this over here. First thing. And then you see the direction, what I have written is like this. The magnitude I have written so much. Should the magnitude be also be here the same? No, it should be much larger. Let me write this a bit larger like this over here. Okay. So though they have not asked it, but strictly speaking, in terms of vectors, okay, you have to write like this, because the force here would be much larger. The force here would be much smaller as compared to this. So when it comes here, what could be the force over here? The direction of the force at position 3. Now it will be in the line joining these two. It should not be perpendicular like this. It should be along the line joining these two, which means it would be like this. Now what could be the length of this vector? Length of this vector should be larger than this and smaller than this, right? So therefore might be I will be able to write little bit bigger like this over here. Okay, or maybe I can extend it even until here. I can extend until here. Okay, the first part is asked only for finding out the forces acting on the alpha particle at positions 1, 2 and 3. We have drawn this. Okay, and then in order to predict the angles between the alpha particles which is scattered, they assume the energy transfer to the gold nuclei with the alpha particles was negligible. Part C to F of this question address the validity of this assumption. Okay, let us when we read the parts C and F, let us come back to this one. The kinetic energy of the alpha particle when it is at position 1 in the diagram is 4.2 MeV. So here it is 4.2 MeV. The energy of the alpha particle is 4.2 MeV. Okay, and then so what? And then show that the energy of 4.2 MeV is equal to 6.72 10 to the power minus 13. So you need to convert MeV into joules. That's the question. So how do I do? So let us write 4.2 MeV can be written as 4.2 into 10 power 6 multiplied by what is m? M is 10 power 6 I have written. E, what is E? 1.6 into 10 to the power of minus 19. Now when I expand, when I multiply all this, simplify it, then I will get to know what is that value. Okay, calculate this here. Let us calculate that value. 4.2 multiplied by 1.6 is equal to 6.72. 6.72 multiplied by 10 to the power of minus 19 plus 6 is minus 13 joules. So this is nearly equal to 6.7 into 10 to the power of minus 13 joules. Right? Okay, let us move on to the next question. The magnitude of the momentum of the alpha particle is given by so much. This P alpha, I'll write this. When it is at position 1, show that. You need to show what is the value of the magnitude of the alpha particle. Now, how do you show this? What is magnitude of the momentum? Momentum of this alpha particle should be equal to m alpha into v alpha. Okay. So do we know the mass of the alpha particle? Mass of the alpha particle is given to you. This is given to you here. What is the velocity of the alpha particle? That is not known. But the energy of it is known. Right? Energy of it is known. So what we will do is, we will relate this one. We will relate P alpha square divided by 2m alpha is equal to energy. Half mv square can be written as P square by 2m. I hope you know this one here. Okay, so if you are not, I can now also write it over here. I can write this as mv square, which can be written as m square v square divided by 2m. And you see m into v is P alpha, 2m I have written as 2m alpha. Okay, so now I want P alpha here. So P alpha would be equal to square root of 2m alpha into E. Now what is the value of E and what is the value of m alpha? So m alpha value is 6.6 into 10 power minus 27. Let us write it down. So this should now be equal to square root of 2 into 6.6 into 10 to the power of minus 27 multiplied by E. What's the value of capital E? The energy of the alpha particle. The energy of the alpha particle we have already written 6.7 to 10 power minus 13 joules. Don't take up this value. Okay, because it's in million electron volt. I want everything in terms of Newton into second. So which is SI unit. So I will keep it only in this way. Okay, so therefore, so let us write down what is the value of 6.7 10 power minus 13. Write down as 6.7 into 10 to the power of minus 13 the full square root, which should now be equal to 2 into 6.6 into 6.7 will now be equal to 88.44 into 10 to the power of 88.44 into 10 to the power of minus 27 minus 30 is minus 40. Minus 40 whole to the power of half. Now I would like to take the root of this one. Root of this would now give rise to 9.4. So 9.4 into 10 to the power of minus 20 Newton second. What is the answer? 9.4 into 10 to the power minus 20 Newton second. Right? So we got the correct answer. Okay, let us move on to the next one. The alpha particle is assumed to have the same speed at position 4. What is position 4 here? Farther away at this position also. It is having the same speed as it has at position 1. So whatever speed it was here, let's say V alpha, the same speed is also seen to be present at position 4. This is your V alpha once again. Okay. So I have written the V alpha direction and also the values also here. I do not know what is this value V alpha. I have just written like this over here. Okay. Then what's the next question? On the vector diagram below, construct the vector representing the change in momentum of the alpha particle between positions 1 and 4. Oh, he has already written this momentum vector. See, this vector is directed like this. See, this vector I wrote it like this. If I multiply this by m alpha, I'll get a vector like that. And this, if I multiply by this, you get a vector like this. Okay, one is towards the left, the other one is going away from here. Okay, so this should be a mv alpha and mv alpha on both the sides. See, one is like this, other one is like this. Okay. Now what is he asking? What is the change in momentum of the alpha particle between positions 1 and 4? Okay, when you talk about change in momentum, let me call delta P. Delta P over here. Delta P alpha I need. Now how do you relate this? This should be equal to final momentum minus initial momentum. Right? Final momentum minus initial momentum. I write P final minus P initial. Now which one is the final momentum over here? This is your final momentum. Right? See, for example, I'll write down this. diagram once again over here. This is my nucleus. This was my first position. It was coming like this. Then it came here like this, and it took a turn like this and went away like this over here, right? So this was your final momentum. This was your final momentum, and this was your initial momentum. This was your initial momentum like this over here. So final momentum minus initial momentum. What is this final momentum? This was your P4, and what was this? This was your P1. Now what is P4? P4 was seen to be m times V alpha. Okay, m alpha times V alpha. And what is P initial? This is m times V alpha. M alpha V alpha. Should I cancel it? No, I should not cancel it. Why? What is the reason? The reason is because they are not along the same direction, right? There should be some vector here. This is one vector here which is directed in a different way. There is another vector which is directed in a different way. Okay. So therefore, now this vector and this vector are different. You cannot cancel V alpha and V alpha here. This is directed along some angle over here. So it is like this over here. So what I will do is, I will not write like this. Okay. If I write like this, it will confuse you. So what I will do, I will just write this as equal to P4 minus P1 over here. Okay. Now this is your P4, and this, what is this? This is your P1 over here. P1 over here. If this is P4 and P1, now what I have is, here I have P4 minus P1. I want to write a vector which is P4 minus P1. See, if I write like this, see, P1 is in this way, minus P1 should be like this. Minus P1 should be like this. Am I right? Minus P1 should be like this over here. Minus P1 is like this. If I have minus P1 and plus P4, which will give me this. What does it give you? It gives you the resultant. Resultant of minus P1 plus P4 would be this vector. Do you agree? This should be your delta P alpha. See, minus P1 plus P4 should be equal to this one. Triangle law of vector addition. We have done this over here, right? So you get delta P alpha here. Okay, so we have drawn this. Next, drawing the spacer side of the vector diagram, a vector representing the momentum change of the gold nucleus. Now you need to write for the gold nucleus when the alpha particle moves between positions 1 and 4. Now what have we written over here? We have written it only for delta P alpha. Okay. Now what happens to gold nucleus? Do you think the gold nucleus will be staying here? Gold nucleus will not stay, right? Because there's a head-on collision here. Collision doesn't mean the two particles should come and have a physical contact between them and they hit it and then move. But instead, as this comes nearby, this will now experience a force, right, due to this alpha particle, and this would also slightly move away like this over here, right? So as the particle moves like this, when this will experience a force in this way, the alpha particle will experience a force outward like this, this particle will also experience a force. Nevertheless, the force which this particle will experience would be very, very small. Okay, but now what can happen? If that is the case, according to Newton's third law of motion, the force that you get here, let me call this as a F alpha particle due to the gold nucleus, and this one is F gold nucleus due to the alpha particle. These are equal and opposite. Why equal and opposite? Because Newton's third law, right? Newton's third law tells you that the action and reaction should be equal and opposite. So they should be equal and opposite, which means what? If I take one of them to be positive, this should be negative over here. So what I can do is, I can now write F gold alpha, F gold comma alpha is equal to minus F alpha comma gold. I can write like this over here, or maybe I can put this negative sign that side also. Anyway, it's fine. Okay, I prefer to write like this. Okay, so anyway, you can write the other way also. Now this one, as we know from Newton's second law, I can now write this as a delta P gold alpha divided by time t is equal to, I'll just erase this. Oh, we are having a lot of space crunching over here. I'll put like this over here. Is equal to delta F alpha comma gold divided by t. Delta P alpha. Okay, delta P alpha. So delta P gold comma alpha divided by t is equal to minus delta P alpha comma gold divided by t. Right? I am just replacing this F by delta P by delta t, which is Newton's second law, rate of change of momentum. So when I do this, then this time and this time goes away. So I am getting this value here, which tells me, what does it tell me? It tells me that delta P gold comma alpha is equal to minus delta P alpha comma gold. Now If I draw, what does it tell you? Now P is a momentum vector. If I draw the momentum vector like this for alpha particle, then for the gold vector, this should be like this over here. That should be equal and opposite over here, right? That's what it tells you. Now let us look at how is the delta P written. Delta P for alpha is written in this way. See in the diagram, it has been written like this, upwards. So how should delta P for this one gold be? I will just erase this one so that this becomes more clearer for me. Okay, so just erase this so that I can write it over here. Okay, let me rewrite it once again. So this should be your delta P alpha. Now for your gold, it should be opposite to this vector. So it should be like this, but the arrow directed like this. So this should be delta P gold. Okay, this is what you are expected to write. Okay, next. See how nicely the same question, vectors, how it has been utilized, has been shown over there. Okay, question E. For the scattering event shown in the diagram on page 8, calculate the recoil kinetic energy of the gold nucleus. Okay, now what we do is, we need to find out the recoil kinetic energy. Now how do we find recoil kinetic energy of the gold nucleus? What is the formula? The formula is half m gold into V gold the whole square. That's what you have to do, not whole square, V gold square. This is what you need to do. So half mv square I need to find, simple. Now is the value of m gold known to me? That's the question we need to ask. M gold is already given to me. M gold is given here. What is V gold? V gold I do not know. Okay, I need to find out that value. So towards it, now if you look at this, for a simple momentum drawing figure, there's two lines which are being drawn, very big ones. What is the need for it? There's some question over here, something related to it. Some clue is given here. Now let us read the question once again. For the scattering event shown in diagram on 8th page, calculate the recoil kinetic energy. So what we do is, here you see there's something like scale 1 centimeter represents 1 into 10 power minus 20 Newton second. Some information is given. Okay, so whenever there's a big diagram given there, something you need to measure and something you need to calculate. That's what it means actually here. Now what you do is, you take a scale here, you measure this distance, or maybe you measure this distance. I don't even need that one. I would like to measure from this point to this point, the whole length of this line that I have drawn. Because if I am doing in an exam, I'll take a scale and properly put it over here. When I measure this length, I find it out that my value, as I see in this paper, I see that this value comes out to be around 11.6 centimeter. The length, okay, in my paper comes out to be around 11.6 centimeter. 1 centimeter represents 1 into 10 power minus 20. 11.6 centimeter represents how much? This should be 11.6 into 10 power minus 20 Newton second. What is this? This is nothing but P alpha, delta P alpha, delta P gold. Momentum we have got. Okay, change in momentum we have got. So what we will do is, we will write delta P alpha or delta P gold is equal to 11.6 into 10 to the power of minus 20 Newton second. This is from diagram. This is from diagram, finding the length. Finding the length of the line. Length of the line. We have now got this one here. Now what's the next step? Now when we have got this one, what is P alpha or P gold? Now we want V gold here, right? Let us now focus only on P gold over here. What is delta P gold? Delta P gold is nothing but M gold into V final minus V initial for gold, right? What is V initial for gold? V initial for gold is 0. Why is 0? Because the gold nucleus was stationary before the collision. So it was 0. So then a recoil happened. So this is your V alpha. So therefore, sorry, V gold. So V final of gold will now be equal to 11.6 into 10 to the power of minus 20 divided by M gold, which will now be equal to, how much is it? Let us find out what is the value of M gold. M gold value is given here as 3.2 into 10 power minus 25. Let us write down that 3.2 into 10 power minus 25. So I will write here as 11.6 into 10 to the power of minus 20 divided by 3.2 into 10 to the power of minus 25. I think it's minus 25 only. Let me check it out once again. If I make a mistake here, yes, minus 25 kg. Right. Now let us find out what is that value. Now 11.6 divided by 3.2 will give rise to 3.625. So I get the answer here as 3.625 into 10 to the power of minus 20 plus 25 minus 25 goes upwards plus 25. 25 minus 20 is plus 5. Wow, this is the speed of the gold nucleus. Okay. Now if this is the speed, now what do I need? I have got M alpha, I got V alpha, sorry, V M gold and V gold. So what is it I need? I need kinetic energy. How do you find kinetic energy? Kinetic energy is equal to half mv square. Substitute all the values. It should be half into, what's the value of m? M value is 3.2 into 10 power 3.2 into 10 to the power of minus 25 multiplied by V alpha. Now V gold. V gold, what is V gold? 11.6 into 10 to the power of minus 20. Sorry, 3.625. 3.625 into 10 to the power of plus 5 the whole square, which should now be equal to how much is it? 3.625 into 3.625 multiplied by 3.2 divided by 2. I get this as 21.025. Let me write it down. This is equal to 21.025, right? I'll write 03 into 10 to the power of, here I get 10 power 5 whole square would be 10 power plus 10 minus 25 should be minus 15 over here. Unit joules over here. Let me check out whether we put the right answer. 21 into 10 to the power of minus 15 joules. Yes, 21 into 10 to the power minus 15 joules is the right answer. Okay, next. From your answer to part D, show that the Geiger and Marsden wave justified in making the assumption that alpha particle loses negligible energy during the scattering process. It means what? It loses energy, but it's very small. So how do you prove that? Now what is this now? This is your kinetic energy gold. Your kinetic energy gold. So what we will do is, we will just take the ratio of kinetic energy of gold divided by kinetic energy of the alpha particle. That's the initial energy, right? So when I do this, 21 into 10 power minus 15 divided by kinetic energy of alpha particle. What is it? We have already found out that somewhere in the beginning. So this should be somewhere over here, right? It was given as 6.7 into 10 power minus 13. We'll take that value also here. We'll write this as 6.7 into 10 to the power of minus 13, which should now be equal to 21 divided by 6.7 will be equal to 3.13 into 10 to the power of minus 15 plus 13 will be minus 2. The ratio comes out to be around 0.03, right? And if I, so what is this now? The ratio here, if I take it as a percentage, this comes out to be around 3%. Okay, what does it tell you? That means the alpha particle doesn't lose much of energy. So according to it, it loses only 3% of the energy while, okay, it passes through the nucleus. Not passes through the nucleus, it gets a head-on collision with the nucleus, it gets deviated. Only this much amount of energy has been lost. So naturally you can say almost, okay, the energy that is being scattered is almost completely negligible, right? So we are able to prove this also. Then you need to write down that argument. Okay, so you can say, you cannot stop over here for 3 marks. You have to first show this ratio, then you say this is 3%, okay, and then you should say alpha particles energy lost is very small or negligible as compared to that of the total energy of the alpha particle. It is only lost 3% of it. Okay. See, how do I know 3%? If you ask me this, you can just say kinetic energy of gold is equal to 3% of kinetic energy of alpha particle. So what does it tell you? That means the gold did not have enough energy. It was zero energy. Okay, it was just staying there. When this alpha particle came and hit over here, so it just passed away like this. What happened? Part of this energy was transferred to the gold. Now you are asking, what is the energy transferred to the gold? The energy transferred to the gold is only 3% of the kinetic energy of the alpha particle, right? So that's what it says. So that means 97% of the kinetic energy of the alpha particle is still there with the alpha particle only. Okay, 97% of the energy of the alpha particle has not been lost. Only 3% has been transferred to the gold nucleus. Okay, now let us move on to the next one. The next section is for the closest approach of a gold nucleus. Don't worry about the term. So let us understand what does it tell you. Diagram shows that the alpha particle follows a head-on collision with the gold nucleus, something like this. What is head-on collision here? The alpha particle comes directly over here. It doesn't go like this, but it takes a U-turn and goes back in the same path. Okay, but in order to happen this one, the minimum distance which an alpha particle can approach a gold nucleus is d. Now let us read the question. Let me assume you do not know anything in nuclear physics and you are completely new. You know only about the mechanics and electrostatics. We are solving this problem only from this point of view. The kinetic energy of the alpha particle when it is far from the gold nucleus is 4.2 million electron volt, which means what? Here is a when it is far. When it is far means where is it saying? He is saying at this point 4.2 million electron volt. This is the energy. The distance d on the diagram represents the closest distance of the alpha particle to the gold nucleus as measured from the center of the gold nucleus. Which means what? This alpha particle which has 4.2 million electron volt, what kind of energy is this? This will be your kinetic energy, which is already told over here. Which means what? The particle is now moving. Now you found out what is the kinetic energy here. Now as the particle starts moving near and near, what happens to kinetic energy? Kinetic energy becomes nearly 4.2 becomes 4, 3.8, 4, 2.6, 2.1, 2, 1, then it becomes in kilovolt, electron volt. Finally, when it reaches here, what happens to kinetic energy? Kinetic energy becomes 0. Why should kinetic energy become 0? If at all, if kinetic energy was there, then what would have happened? It would have gone directly inside the gold nucleus and bumped it over, right? But it did not bump, right? It had kinetic energy equal to 0. It is similar to saying that you take a particle, throw it upwards. What happens? Okay, in your hand, it had a lot amount of kinetic energy, and as it started moving upwards, then the kinetic energy gradually starts reducing. When it goes to the maximum height, the kinetic energy becomes 0, and then once again kinetic energy rises. So the same thing is happening. Okay, that's this. The same thing is happening over here. Only thing is here it's happening horizontally like this and not vertically. Okay. Now explain what has happened to the kinetic energy of the alpha particle when it is at a distance d from the center of the nucleus. Now I told you the whole story. Now what is it you need to write? You need to write 3 points over here. 3 marks, 3 points over here. What happens when it is at a distance d? First point tells you the kinetic energy of the alpha particle tends to be 0 or becomes 0 over here when it is at a distance d. Second point, if it becomes 0, what's happening to that? Is there a friction there? Okay, there is no friction, right? Then what happens to the kinetic energy? Why should it become 0? Because we know energy cannot be created, not be destroyed, it can be transferred. Now what is the transfer? Where is the transfer happening? Somewhere this kinetic energy should have got transformed into something, right? What is it happening? Kinetic energy of the alpha particle has got converted into potential energy of the alpha particle. How do you know potential energy? Because you know potential energy of a particle is given by kq divided by d, right? You know this in electrostatics, right? Already learned this. So potential energy is kq1 q2 divided by d. This is only potential. Potential energy is kq1 q2 by d, where k is nothing but 1 by 4 pi epsilon naught into q1 into q2 divided by d, where q1 is the charge due to gold nucleus, and q2. What is q2? q2 is the charge due to alpha particle. Okay, so thus you can find out what is this value. Now we have put 2 points over here. Now what happens to what's the third point over here? So as a result of it, okay, it takes an U-turn. So this is what you need to mention. So now, the third point, you need to write down the third point over here. Okay, such that, so kinetic energy gets converted into potential energy such that total energy is conserved. You need to mention all this. Okay, you get 3 marks over here. Now let us move on to the last part of it. Determine the distance d of the closest approach. Atomic number of the gold is 79. What do you mean by atomic number? Number of protons is equal to 79. This is known to you. Now what we need to do? We will apply this formula, right? This formula will apply. Okay. So towards it, we know half m alpha v alpha square, okay, which is nothing but what is the kinetic energy of it? It's already given to you. How much is it given? 4.2 million electron volt. Okay, so this was the initial energy, which was 4.2 million electron volt, should now be equal to k q1 q2 divided by d. Okay, let us equate this and do this. Is 7 marks over here. Okay, let us do this one. Determine the distance d. Okay, so now what we do is we'll write this as 4.2 MeV. I'm not going to change anything here for some reason. We'll write this as K into what is Q1. See, this is your gold, which had 79 protons. This is your alpha particle, which had 2 protons and 2 neutrons. What's the net charge on it? It has only 2 protons, which is 2e here. 2e here. What's the charge on this one? This is 79e over here, right? So I'll write Q1 should be equal to 79e, and what is Q2? 2 times e divided by d. Okay, now I hope everything we have written over here, right? I need to substitute the value of k also. Let us do that also. So I will now write this as, what is the value of k? Electrostatic constant, 9 into 10 to the power of 9, which you already know, multiplied by 79 into 2. 79 into 2 multiplied by e into e square divided by d, which should now be equal to, here also I'll write 49 into 10 to the power of 6, not 49, sorry, 4.2 into 10 power 6 into e, and I'll write only so much over here. The reason is I can cancel this e and this e over here. Next, what I can do, I need to get the value of d. So I'll write d is equal to 9 into 10 power 9 into 79 into 2 into, and now I have this lone e, I'll substitute the value of e, 1.6 into 10 to the power of minus 19 divided by 4.2 into 10 to the power of 6. Now let us do the math over here, and whatever is the answer, that gives the value of t. Now let us do this math, find out what is the answer we get. Okay. Okay. Now we have 9 multiplied by 79 multiplied by 2 multiplied by 1.6 divided by 4.2. I just taken only the numbers, then I will multiply this. I'll take the power of 10 later on. I get this answer as 541. 541 point, what's the point over there? 71. I'll take it as 7 multiplied by 10 to the power of 9 here. This is 6 over here. This becomes 3. So I'll write it as 9 minus 19 minus 6. How much will this be? This will be 541.7 into 10 to the power of minus 9 minus 19 is minus 10. Minus 10 minus 6 is minus 16 over here. Minus 16 meters. D is meters, right? So which should now be equal to, if I write it properly, I can write this as 5.4 into 10 to the power of 2 spaces, 2 dots I move to the left, so this will become minus 14 meters, right? So thus, what does it tell me? It tells me, let me check out the answer properly. 5.4 to go minus 14 meters. Okay, what does it tell me? It tells me that the alpha particle with a hefty amount of kinetic energy would still be able to come until a distance of 5.4 into, this distance would be only around 5.4 into 10 to the power of minus 14 meters. It comes until here, and then it rebounds and goes backwards over here, right? So we have seen all the concepts being properly covered. Okay, let me just enumerate or let you know what concepts we have done. We come to the end of the question. The first concept that we learned here is about how to draw the vectors. Okay, and we also came to know how the repulsive forces are being acting onto it, and how to draw the vectors, what are the magnitudes of it, okay, how to draw the magnitudes, increasing magnitudes, decreasing magnitudes, and how should the vectors be drawn at every position. Then the second question here focused on how to convert an energy into joules, energy which is mentioned in electron volt, to convert it into joules over here. So what is the formula we use over here? We use the formula energy or W work done. We have learned this in electrostatics as Q times V, right? Q is the charge, V is the potential difference, right? So we use the same thing. See, V is the potential difference. This whole thing is nothing but your charge over here. This is your Q over here. Q times V. Okay, this is what we have learned here. And the third concept we learned here is how do you find out the momentum using the energy, okay, which is P square by 2m equal to a kinetic energy. Making use of this, you are able to find out this value here. Then the next one which we have used is Newton's third law. See, suddenly it jumps to one chapter to another chapter. So how do you use it? Using the vector diagram we have found out. And how do you prove the Newton's third law? Using Newton's third law, how do you find out what is the momentum change in the alpha particle and gold particle? Or in other words, when you have two masses, when they hit with each other, how is the conservation of momentum taking place? Okay, that's what has been observed here. And then the next one is about which is this? Yeah, this we have seen. And the next one is about, we have seen about how do you find out the momentum, how do you find out the velocity of the nucleus, and how do you find out the recoil kinetic energy of the another particle. Okay, when there is a momentum transfer or when there is a collision being seen, so there is a recoiling effect being observed. How do you find out the kinetic energy of it? How do you find the velocity of it? We observed all this over here. And after that we looked at, okay, so how do you justify that the particle which was a small particle which came and hit a massive particle over there, okay, so then how much energy was being transferred to it, okay, has it really lost some amount of energy, or what has happened to the particle? Okay, so this we were being able to justify. And it tells you about whenever you have studies related to something like exchange of momentum, then how do you relate the energies, okay, and how do you say that there was an elastic scattering or there was an inelastic scattering? What makes you think things like this happens? Okay, from the research point of view, these kinds of questions can be answered using this kind of approaches. And then finally we looked at, okay, a head-on collision with a alpha particle with a gold nucleus. Then you found out like what was the minimum distance, okay, and how this is related to gravitation, similar to, so I'm not saying gravitation and this is completely the same, okay, it's totally different, but still what I'm saying here is that you see that whatever process happens there, as an analogy we found out what happens then vertically, the similar thing happens, not same, similar things happens here also, and we found out what is the value of D. Okay, so thus we found out kinetic energy gets converted into potential energy, conservation of energy we have seen over here, and finally we found out what is the distance of closest approach. Okay, the entire thing of nuclear physics in Rutherford model has been covered totally, only making use of mechanics, then electrostatics and vector diagrams. Okay, I hope you have enjoyed doing this question. Okay, if you have not done it, so please redo it once again, so you will understand how to solve such kinds of problems. Thank you for watching. So tomorrow we will see you in the next video. Thank you.